Hello, everyone. Today we're going to be going over an organic chemistry question. I got this one from Jack Westin. I thought it was pretty good. We can also go over the mechanism of this reaction as we proceed. So the question is, the aryl halides p-chlorotoluene and m-chlorotoluene, which contain a methyl EWG or electron withdrawing group, are shown below. When p-chlorotoluene and m-chlorotoluene are reacted with NaOH, sodium hydroxide, how many products are produced respectively? So let's kind of go over what would happen if we somehow decided to do a nucleophilic aromatic substitution. This is what this reaction mechanism basically is. So this is a nucleophilic aromatic substitution. And there are two types of nucleophilic aromatic substitution. The first one, where you have an electron withdrawing group that kind of parks the electrons, and another one is the formation of this thing called a benzyne. Because here, there really isn't a place on any of these molecules to exactly park an electron. We have to use the benzyne method. So what is a benzyne? A benzyne is basically a benzene, except it has a triple bond here. And this triple bond makes it really, really reactive. So why don't we go over the mechanism of figuring out the products of para-chlorotoluene? So the first thing we do is we start with para-chlorotoluene. And what happens is we're taking in a sodium hydroxide. And what is it going to do? It's going to take a hydrogen. It could be this hydrogen, it could be this hydrogen, it really does not matter. This hydroxide will come in, it will basically steal this H. This red bond over here, this H, will break. And in the same process, it will give this bond over here will kind of go to the chlorine and kick it out. So now what happens? You have your methyl group still there. That hasn't changed. The benzene rings aromatic bonds haven't changed. But we now have this new extra pi bond that should not be there. It really doesn't want to be there. So what is it going to do when you're in sodium hydroxide? So what ends up happening is you actually end up adding another hydroxide to this part, to one of the carbons. It really does not matter. This is not sterically hindered. So what can happen is that as soon as you add to one carbon, the bond in red, that pi bond, will kind of be pushed to the other carbon, and it will give it a negative charge. So what will then happen is I now have a negative charge and I have a hydroxide over here. And I have this negative charge over here. And similarly, with the bottom product, you have something kind of similar, except here you have a hydroxide down here. And the negative charge is down here. So in the first case, the hydroxide is meta to the methyl group. In the second case, the hydroxide is para to the methyl group. So what then happens, carbons really don't like to be bases. So it's going to take a proton from something willing to give it. We're in base, so this in hydroxide solution, so the strongest acid that can be in a hydroxide solution is water. So the lone pair on the carbon will basically steal that H, that proton, from the hydroxide, or from the water, and forming a hydroxide. So you'll form this product over here, and here you're going to form this product over here. So if you kind of look at the mechanisms, call this M-methylphenol, or like meta-methylphenol. Or you could, in theory, just call it, I think this is a cresol bifunctional group. But basically, this is kind of what you get. You get two different products. If we were to try a similar example with the metachlorotoluene over here, if we tried a similar example with this metachlorotoluene, what can happen is that when the hydroxide comes in, it could steal an H. It could steal an H from here, forming a benzene over here, or it could steal an H over here and forming a benzene over here. So when that happens, you can actually get two different benzenes. So you get two different benzenes over here. And just for clarity, I'm going to draw the benzene like this, where the bond that we want to react away is going to be shown in red. All right. And the benzene, this benzene over here, can basically add itself wherever it needs to, right? Like it can add itself either on this carbon or this carbon. Another hydroxide can add on either of these carbons. Similarly, the hydroxide can add on this carbon or this carbon. If the hydroxide were to add on this carbon with the blue arrows, following the mechanism before, you would end up getting something like this. You would basically get the meta product again. All right? If the hydroxide added there, or if it added there, then you could, in theory, also get the para product, or you could get the ortho product. So this cumulatively actually has three different products that can be formed from this reaction. All right. Thank you very much for coming. Have a great day.